Imagine the universe as a grand cosmic symphony playing for nearly 14 billion years. Everything we see and are is part of this music, from galaxies to atoms. This symphony is conducted by just four fundamental forces, rules that govern every interaction in the cosmos. They are the invisible strings that pull the universe together, and sometimes push it apart. For centuries, we thought these four were the complete orchestra. But what if there's a hidden instrument, a fifth force playing a subtle, mysterious tune? Scientists are listening closely, searching for something new. This quest is driven by strange clues and puzzles the four known forces can't solve. The universe, it seems, still has secrets. The search for a fifth force is one of the most exciting adventures in modern science. It challenges the Standard Model, the most complete theory of particle physics ever devised. The Standard Model is a monumental achievement, but it has gaps. It doesn't include gravity or explain the biggest cosmic mysteries. The discovery of a fifth force would be a revolution, opening new pathways to explore the deepest questions about our universe. Let's start with gravity, the force that keeps us grounded and shapes the cosmos. Newton described it, but Einstein revealed it as the curvature of space-time itself. Massive objects warp space and time, guiding planets and stars in their paths. Gravity sculpts galaxies and clusters over billions of years. Next is electromagnetism, the force behind light, electricity, and magnetism. It holds atoms together and powers everything from rainbows to smartphones. Electromagnetism can attract and repel, carried by photons, the same particles that make up light. Gravity is incredibly weak compared to electromagnetism. A fridge magnet can overpower Earth's gravity on a paperclip. Yet gravity dominates on cosmic scales because it always attracts, while electromagnetism's charges often cancel out. Together, these forces paint the picture of the visible universe, explaining orbits, stars, molecules, and light. For a long time, we thought these two might be all we needed. But as we looked deeper, we found the story wasn't over. Two more forces were waiting, hidden in the subatomic realm. The symphony had more instruments, stranger and more powerful than we imagined. The universe's balance depends on all four. Now let's dive inside the atom into its dense core, the nucleus. Protons, all positively charged, should repel each other, yet the nucleus holds together. The strong nuclear force is the cosmic superglue, binding quarks into protons and neutrons, and those into nuclei. It's the most powerful force, but only works over tiny distances. Without it, there'd be no atoms beyond hydrogen, no elements, no chemistry, no life. The sun's fusion is powered by the strong force, converting mass into the light and heat that sustain us. Then there's the weak nuclear force, the strangest of all. It's weaker than the strong force in electromagnetism, and also acts only at subatomic scales. The weak force changes one particle into another, enabling radioactive decay and powering the sun's reactions. Without it, the elements essential for life would never have formed in stars. So gravity shapes galaxies, electromagnetism lights our world, the strong force builds matter's heart, and the weak force lets it evolve. For a while, this quartet seemed to explain everything, but the universe is full of surprises. Our theory of four forces is impressive, but it leaves huge gaps. Dark matter is the biggest mystery. We see its gravitational effects, but not the matter itself. It makes up about 85% of all matter, yet we have no idea what it is. Then there's dark energy, discovered in the 1990s, pushing the universe apart and making up 70% of its energy. The matter and energy we understand account for only 5% of the cosmos. The other 95% is a mystery. These cosmic puzzles hint that our story is missing a major character. The search for a fifth force is also driven by tiny anomalies in precise experiments on Earth. Sometimes particles don't behave as the Standard Model predicts. These are subtle, persistent deviations, like a faint discordant note in our symphony. They could be signs of a new, undiscovered force. A fifth force might interact with dark matter, explain dark energy, or account for these experimental anomalies. Finding it would be like discovering a new continent on a map we thought was complete. The universe is telling us our understanding is incomplete. The quest for a fifth force could unlock the next great chapter in physics. So what might a fifth force be like? Scientists have many ideas, but no firm answers yet. One possibility, it connects our world with the hidden world of dark matter, a cosmic bridge. It could be carried by a new particle, like a dark photon, acting as a messenger between the known and unknown. Maybe it's a modified version of a known force, or a new, very weak force that only appears under special conditions. It might be incredibly short-ranged or so weak that it's drowned out by the other four. Some experiments suggest it might not treat all particles equally, interacting differently with electrons and muons. That would break a key symmetry of the Standard Model and open the door to new physics. Discovering a fifth force would mean finding a new fundamental particle, the smoking gun. The search is on for both the force and its carrier. This is the great treasure hunt of modern physics. Reality may be far richer and more complex than we ever knew. How do you find something so elusive? By building the most powerful machines ever created. Around the world, giant experiments push the boundaries of knowledge, searching for cracks in the Standard Model. The Large Hadron Collider at CERN smashes protons together at near-light speed, recreating the early universe for a moment. By sifting through the debris, physicists look for new particles or unexpected decay patterns. The LHC is famous for discovering the Higgs boson, but its search for new physics continues. Precision experiments measure particle properties with incredible accuracy, hoping to spot tiny deviations. Some labs are deep underground, shielded from cosmic rays, searching for direct interactions with dark matter. Others use lasers or magnets to probe the vacuum itself. Each experiment is a different way of asking, is there anything else out there? It's a global effort, uniting thousands of scientists in the quest to see beyond the known horizon. One of the most tantalizing clues comes from Fermilab's muon G2 experiment near Chicago. A muon is like a heavy electron, and when placed in a magnetic field, it wobbles. The Standard Model predicts this wobble with extreme precision. But the experiment finds muons wobbling just a bit faster than predicted. A tiny difference, but huge in physics. The leading explanation: undiscovered particles or forces are at play. As muons travel, the vacuum is a bubbling soup of virtual particles, some possibly unknown. If a fifth force exists, its carrier particles would add an extra push to the muon's wobble. This isn't definitive proof yet, there's still a chance it's a fluke or a calculation error. But as more data comes in, the measurement grows more precise. If the discrepancy holds, it could be the first experimental evidence for physics beyond the Standard Model. It would be a powerful pointer toward a fifth force. Imagine the evidence becomes undeniable. A fifth force is discovered. Physics would be revolutionized, the Standard Model proven incomplete. Scientists would race to understand the new force, its strength, range, and connection to dark matter. It could finally reveal the true nature of dark matter, transforming cosmology and our models of the universe. This knowledge would ripple outward, changing our understanding of galaxy formation and cosmic evolution. Beyond science, a new force could lead to technologies we can't yet imagine, just as electromagnetism powers our world today. It might unlock new energy sources, propulsion methods, or materials. Most importantly, it would remind us that reality is deeper and more complex than it appears. Discovering a fifth force would open a new dimension of reality to explore. It would inspire a new generation to ask big questions. It would be a shared human achievement, a moment of collective discovery. The universe would be revealed in a new light. We live in a remarkable time, perched on the edge of a possible scientific revolution. The puzzles of dark matter, dark energy, and experimental anomalies are calling out for answers. The scientific community is abuzz. Are these clues leading to a dead end, or a new understanding of the cosmos? The path forward is clear but challenging, requiring patience, precision, and perseverance. Experimentalists must gather more data, theorists must develop new models. Science advances not in a single eureka moment but through the dedicated work of thousands. There's no guarantee of success, the anomalies may fade, or the answers may lie elsewhere. But the search itself enriches our knowledge and capabilities. The hope remains that we're on the brink of a new chapter in our cosmic story, a discovery that could rewrite textbooks and reshape our view of reality. The universe is not a solved puzzle but a living mystery inviting us to look deeper. The cosmic symphony is still playing and we're learning to listen for new notes. The next great leap in understanding could be just around the corner.